Okay. Going to finish up the serve script.r file today. Last time we saw how to do maximum likelihood estimation of a survival function, a survival curve. So we now know two different ways to estimate a survival function. One is Kaplan-Meier, which is a non-parametric way. That's the step function way. And if we're willing to hypothesize a distribution for the actual survival times, then we could use likelihood-based methods and get a maximum likelihood estimator. So here is what we figured out was the likelihood for right-censored data. It's a product, like likelihoods have been for us. We are assuming independent observations. So a likelihood, which is roughly speaking a joint probability of the data we observed, is just a product. And then the detailed issue is, what do we put in as the product pieces? There's two different types of contributions to the likelihood. There's one for uncensored individuals, and there's one for censored individuals. Okay. So back in the script, we simulated some data. Let me go ahead and re-simulate these data. This is a sample of size 100, and I'm going to randomly pick some proportion of the individuals to be censored. Okay. And then we could fit the Kaplan-Meier curve using the serve fit function. And we could do maximum likelihood in two different ways. The first way we did it was to do a grid search. We have two parameters for the survival probability distribution. There's the mean and there's a standard deviation. So one way to do a maximization exercise is to consider a variety, like a partition of values for the parameters of interest. That's what we did initially. Let mu be a partition from 3 to 7. Let sigma be a partition from 0.75 to 2.25. And then we can evaluate the log likelihood at every pair of possibilities, and then figure out which pair gave us the biggest likelihood. That's not the most efficient way to go about doing maximization of a likelihood. So what we did next was use the optim function. This was my function for evaluating the log likelihood. And then down below, we used optim to maximize that function. Remember that optim actually does minimization of an objective function. So in order to use optim to get maximum likelihood estimates, what we did was pass it the negative log likelihood function. So please minimize the negative log likelihood, which is equivalent to optimize or maximize the log likelihood. When we use optim, we have to provide starting values for the algorithm. And the way we did that was just compute the kind of naive mean and naive standard deviation, ignoring the censoring. Yep.
Why do you have return?
Right here. This actually could be gotten rid of. If you create a function like f is a function of an argument x, and maybe you do inside this x is x times 2 minus 4, and you want to return that value of x. If I want, after calling this function, to have the result returned to me, I can do one of two things. I can say, make the last line of the function be just the name of the thing I want spit back to me. That is equivalent to saying return that object. I like using return just because it seems like the most readable way to write it. But whenever I say return something, that's all that is saying give it back to assign it to this object, for example, after calling the function. Okay. All right, I'll remake the picture that we saw last time that compared Kaplan-Meier to MLE. Kaplan-Meier is the step function with the confidence bounds, and the red smooth curve is a normal survival function where we've plugged in our estimated mean and standard deviation of the normal. Once we have estimates of the parameters, we can draw any function that we want. Couple of other summary statistics that are useful with survival data. One is the mean survival time. So instead of a whole survival curve, can you compute an estimate of the average survival time? Among all the people with HIV in our study, what's the average time until death? There's a couple of ways to compute that. There is a result that says if we have survival times t according to some distribution f with parameters theta, the expected value of t is equal to the integral of the survival function. It just turns out that that's true. Since in survival analysis we're often working with a survival function or an estimated survival function, if I want to translate to an average survival time, I can work with the survival function. So to compute mean survival time, it turns out that the mean survival time is defined as the integral of the survival function over its entire support from 0 to infinity. One way we could estimate that is by going to our Kaplan-Meier curve, and an integral, is an area under the curve. With a step function, that's really easy to approximate. If I want to estimate the mean survival time, I can add up the areas under the Kaplan-Meier curve. So, for example, if we had a step function like this, the integral of it would be this width times this height plus this width times that height plus this width times that height, this width times that height. So just sum up the areas of the rectangles underneath the step function. This code does that. What I'm going to do is accumulate from the left height of the rectangle. I'm sorry, this is height of the rectangle, estimated survival function, times width of the rectangle. So we're just working our way from the left all the way across the Kaplan-Meier curve, height of each rectangle times width of each rectangle. The last highlighted line is a shorter version of the same thing. But either way we do it, we have an estimated average survival time of 5.423. With a parametric survival function, we would have to actually integrate it. There is a function in R called integrate that makes that easy. So I'm going to integrate. I really want to do this from 0 to infinity. I want to integrate the survival function, 1 minus the normal CDF, because this simulation is assuming the survival times are normally distributed. So you tell me what the estimate of mu and sigma are. 1 minus p norm, plugging those values in, is the parametric survival curve estimate. So here I'm creating a function called surv_f that evaluates that parametric survival curve, and then we will integrate it from 0 to infinity. Pretty close to the estimate from the Kaplan-Meier curve. So mean survival time is useful. So would be median survival time or any percentile. So for example, the median survival time, how could we get that? The way we would define it is median survival time is the minimum time for which the survival probability is less than or equal to 0.5. So where is it that, what time point is it that the survival time, the survival probability is less than or equal to 0.5? The survival curve drops down from 1 to 0 with an S-shaped pattern. So we're looking at where is the first time that it has dropped to or below 0.5. Median survival time, according to our fitted model. Here's one way to do it. This just puts into action the definition from above. Go find the minimum time such that the fitted survival probability is less than or equal to 0.5. The same findings can come straight out of the surv_fit report. If you print summary of a surv_fit object, part of the output is survival probabilities next to every unique event time. So I could come through this output and just scroll down until I see the smallest time such that the survival probability is less than or equal to 0.5. In this case, the median survival time would be 5.52. How does that compare to the mean? The mean was 5.42, so they're pretty close. With a parametric survival curve estimate, you could just ask for a percentile directly. If I'm saying the survival times are normally distributed, and now I have estimates of mu and sigma, I can just ask for what is the median of that corresponding normal distribution. What comes next is a comparison of survival curves. Suppose we have a treatment group and a control group, and we're going to estimate survival probabilities for each. And we want to ask, is there a difference between survival prognosis for the two groups? This is just like what came from above, except now I'm going to have two comparison groups instead of just one population. We'll have 100 individuals in each comparison group. We'll say the means in the two groups are 5 and 6. We'll say both groups have the same standard deviation, that 30% of the individuals in each group are censored. And then here's simulating the data. Here is creating censoring. And here is computing Kaplan-Meier curves. So let's run all of that and then make a picture. This puts both of those Kaplan-Meier curves on the same plot. Looks like that. Group 1 is blue, group 2 is red, and so what we have evidence of is group 2 having the better prognosis, because at every single time the survival probability for group 2 is higher than that for group 1. In terms of comparing survival prognosis, we're interested in who has survival probabilities that are shifted up with respect to the other. That's the group that is in better position, or has better prognosis. If we wanted to test, yes or no, do they have the same survival probabilities or survival curve? This is different from asking whether the survival probability is different at a specific time. This is looking at the entire curves. There is a function, servdiff, and it implements what's called the log rank test. So I'm going to say instead of servfit, servdiff. I again need to wrap my censoring times and censoring indicators into this capital serve object. Notice that what we did up above, I didn't emphasize this a moment ago, but what we did up above was put all of the event times into one object. I have the 100 from comparison group 1, followed by the 100 from comparison group 2. And similarly, we have all 200 of the censoring indicators concatenated together. Inside servdiff, I say, here is my serve object, capital Y and capital delta. And then I want to model it in terms of, instead of putting a 1 there like we've been doing to get a single Kaplan-Meier curve, I put a categorical variable or a factor that says group 1 or group 2. So group would be 1 for the first 100 and 2 for the next 100. Servdiff will give us a p-value for testing whether the two survival curves are the same. In this case, it's not surprising that we got a really small p-value. Those curves are pretty demonstrably different. If they were crossing over each other multiple times, that'd be different. That would be a harder thing to say. But this is very obviously different. Okay. So that's enough about survival curves. Let's change gears and start talking about another summary measure with survival data. And this is going to be our entry point into regression with survival data. I mentioned last week that when we do when we do linear regression, usual linear regression, we're saying that the mean of our continuous response variable is linearly associated with some covariate or some collection of covariates. Then we interpret the coefficients like mean differences in the response associated with a 1 unit increase in the covariate, holding everything else constant. If we do different types of regression, like for example logistic regression, it is a similar idea. We're going to relate a response variable to some covariates by assuming a linear association. But because of the 0-1 nature of success-fail data, when we do logistic regression, we don't try to regress zeros and ones on the covariates directly. So if I had 0-1 data, some continuous covariate x, and my response variable that is either 0 or 1, it's not optimal to try to fit a line to these types of data. They don't conform to a linear kind of relationship. If you fit a line to data like this, in some sense you're connecting them with a pattern, but there's several ways that that's not optimal. For example, the fitted values of that curve are allowed to go outside the range of possible values. You could get negative predicted values, you could get values that are bigger than 1. So what we do instead is we reparameterize, and for our response we use a log odds. Log of p divided by 1 minus p, and this is expected to have a linear relationship in x. So when we do logistic regression, we're essentially trying to do the regression that we're used to, but we're changing the response to make it so that it is a sensible thing. Now that we're looking at survival data, we're going to do something similar. We are not going to have... Okay, there's a couple of ways to do regression with survival data. The way we're going to emphasize does not put survival time on the y-axis and x on the horizontal axis. Instead, we're going to have some new summary measure. Just like logistic regression has this weird summary measure that's the log odds, with survival data, we're going to have a weird summary measure that's called the log hazard. So I will introduce that in 1 second. Before I leave this note, though, let me just say there are regression models that operate this way, that do regress the event time on the covariates. Those are generally parametric survival analysis models. I'll say something very briefly about them at the end of our coverage of survival data. So things like accelerated failure time models are parametric regression models for survival data, and they work directly with the event times. I think it's fair to say, though, that by far the most widely used regression technique with survival data is the Cox proportional hazards model, and it works with hazards. It has the name in the name, hazards. So let's figure out what a hazard is. What is a hazard? The hazard function, h of t, is defined as the density at t divided by the survival probability at t. F of t divided by capital S of t. That looks like a conditional probability, which would roughly be interpreted as the instantaneous probability of death at time t, given that an individual survived up to time t. So it's like a time-dependent quantification of instantaneous risk. Given that you are still alive at this specific moment, what is the instantaneous probability that you will die at this moment? The hazard is a function over time. When it's high, your risk is high. But obviously, it's a little bit harder to interpret than just an event time. It's not just time that you died. It's not mean time that you died. It's this kind of strange quantity, just like an odds is kind of a strange quantity that we work with because of the mathematical niceties of it. So the hazard, think of it like an instantaneous risk at a time t. Even if you can't 100% explain what that means to your grandmother or something, in terms that she would understand, you can say that hazards are, the higher they are, the worse off you are. The higher the hazard, the greater the chance you're about to die. So we're going to work with this thing called a hazard. Here's how we work with it. We're going to say that for an individual with covariates given by xi, that's a vector, so that could be individual i's dosage of the drug, individual i's age, gender, race, could be all the covariates for an individual. The hazard at time t for an individual with these covariates is going to be modeled this way. We're going to model that as a product of what's called a baseline hazard, H0 of t. Note that that does not depend on the covariates, H0 of t, times some other function that does depend on the covariates. That x transpose beta should bring to mind the way we represented regression models early on as y equal x beta plus epsilon. This is like x beta for one individual. We're saying the hazard for an individual with a certain collection of covariates is equal to a baseline hazard that does not care about covariates, that applies to everybody equally, and the only change to that baseline hazard is that we multiply it by some function of the covariates. The specific choice of this function r that's most widely used is the exponential function. That results in this model, and this is called the Cox proportional hazards model. It says hazard at time t for an individual with covariates x is equal to the product of a baseline hazard at time t and some factor that only depends on the covariates. The baseline hazard depends on time, but not the covariates. The other piece depends on the covariates, but not time. So, we are making a simplifying assumption. We're saying hazard, which could depend on time and covariates, can be factored into two pieces. One that depends only on time, the other depends only on the covariates. What's handy about doing that is that now the covariates and the regression coefficients are not time dependent. We're saying that there is a fixed effect of each covariate regardless of time. Like treatment effect is going to be assumed to be the same regardless of time. It is to multiply the baseline hazard by some fixed constant. That's a fairly strong assumption, so we do need to be a little bit worried about whether the assumptions of the model hold. If we have just a two-class problem, treatment and control, say, then individual I can be, their quote covariates are essentially a 1 to turn on the intercept in the model, and a indicator variable for whether or not they're in the treatment group or the control group. So Tx sub I would be 0 for a control individual, 1 for a treatment individual. This proportional hazards model, which says, let me come back to the whiteboard here. Proportional hazards model says that the hazard at time t for an individual with covariates x in the model with coefficients beta equals baseline hazard at time t times e to the x transpose beta. So if x is let's say x is either 0 or 1, 0 if control group, 1 if treatment group, then the hazard at time t for a control, or let's say for a treatment individual, will equal h0 of t e to the beta. Whereas a control individual, h of t for a control individual, would be h0 of t e to the 1. So the ratio that should be e to the 0, which equals 1. So the ratio of these two, the hazard ratio comparing treatment to control, is just e to the beta. The baseline hazard cancels out. Comparing any two individuals at the same time, the baseline hazards will cancel out, so there is no effect of time. All that's left is comparing the beta pieces, the linear combination of the coefficients pieces. So e to the beta for any one beta coefficient is a hazard ratio. Just like in logistic regression, beta is a log odds ratio. So e to the beta in a logistic regression is an odds ratio. E to the beta in a Cox proportional hazards model is a hazard ratio. Again, it's kind of hard to interpret exactly what a hazard ratio is, but it has a odds ratio or relative risk kind of interpretation to it. If my hazard ratio with my covariates is 2 times, or if my hazard is 2 times yours, that's at least a quantifiable level of risk for me. I have twice as amount of the risk that you do in some sense. So, with a Cox proportional hazards model, we are going to interpret the coefficients like hazard ratios. Specifically, e to a coefficient is a hazard ratio, which means that a coefficient is a log hazard ratio. All right. How about we look at an example? Let me find one. I have several survival data examples on eCampus for us. Let's try. Let's try this one. ACTG320, I think, is survival data. And let me see if I have a script. Okay. Okay, so these are survival data. These are AIDS patients in a clinical trial. We have a little over 1,000 individuals. We also have 16 variables. Double-blind, placebo-controlled trial. I'll spend at least one lecture this semester, by the way, talking about study types, like what's a clinical trial? How's a clinical trial different from an observational study? What's a meta-analysis? That type of thing. I do think that's relevant to biostatistics, is knowing like what types of studies are out there and how the different types can be interpreted, what they can and can't tell you. This was a double-blind, placebo-controlled trial that compared a 3-drug cocktail with a 2-drug cocktail. So these were all patients with HIV, or I guess they all had AIDS, full-blown AIDS. And if you're going to do an experiment to assess the efficacy of a particular drug on AIDS patients, it is not ethically reasonable for us to say randomize an AIDS patient to either receive the new treatment or say aspirin. That's not ethical because there are existing treatments that make real world effects. So in those types of settings, you compare newfangled treatment to, quote, standard of care. Here we're going to compare standard of care, which was a 2-drug regimen, to a newfangled regimen which added a drug. Okay, we have descriptions of all the different variables. I'll just go ahead and load them in, and then I want to fit one of these Cox proportional hazards models to show you what they look like. Mm-hmm.
So in this case, would you be able to model the interaction between the standard treatment and new treatment? Because you have to do the new treatment on top of a standard way wherever people do it, right?
Okay. Question was, would you be able to model the an interaction between the two treatments? So let's see what we're doing here specifically. We are comparing IDV, ZDV. Why does it say or? 3-drug regimen of this this or that, and this. Comparing that with zidovine or stravudine and lamivudine. Okay, so the control group is either ZDV or D4T and 3TC. The treatment group is that plus IDV. So the control group, or the treatment group is the control group plus something, as opposed to two completely different comparisons. So I think what you would be doing is citing previous literature that says that control treatment regimen is defensible. It would not be acceptable as a control group if it had not already been shown to have beneficial effects on people with AIDS. So this trial is not interested, the goal was not to evaluate that controlled treatment. It is accepted as the standard of care.
Yeah, but if you get an effect, how do you know if these new treatment you're testing is depending on those control group, or if it has effect itself, right? If you do a clinical trial, it has an effect, it's effective, and now you're applying to a patient with no control treatment, maybe it doesn't have an effect.
Yeah, good. So the comment was, if we did see a difference in this scenario, how do we know that it's the IDV alone and not IDV that's dependent on these other two that are already there? So I don't know everything about this specific setting, but what I would assume is they're testing for should we give people the 3-drug regimen. I don't think they're using this to argue for IDV only. I think they're arguing for let's add IDV to these other two. And if that's the goal, then this would give us evidence, defensible evidence for that efficacy. It is, like you said, a different matter if we wanted to use this trial to argue that IDV should replace the standard of care, because we don't have data to argue for that. It could be that if you pulled out those other two, there isn't, it's not, it doesn't work anymore.
As you know, this is a big problem in the clinical trial. It's non-ethical if you just treat the patients with no control treatment and you just dump whatever new treatment is. That's not ethical to do it, but that always complicates this scenario when the new treatment is depending on the old treatment.
Yeah, that's good.
So, I was just wondering if there's a statistical measurement to separate the two effects, to model if it's there's an interaction environment, if there's a way to test the p-value of that coefficient.
The only way I know how to test that would be to actually do a trial where it was where you pulled out those other two, and you can't, I don't know how you do that, so. Maybe you start with animal models, you have evidence that IDV plus these two does something. Well, I wonder if IDV only does something. You obviously would not do that in humans initially, but you could do that in animals. And if you have strong animal model results to point to it, then you could build on that and hopefully ultimately consider what you were describing, IDV only. Let me fit one Cox proportional hazards model and just show you what the output looks like, and then we'll quit for the day. We have a treatment indicator. Is it control or is it treatment? So is it the 2-drug cocktail or the 3-drug cocktail? And we're going to fit a regression model, a Cox proportional hazards regression model, survival time related to that covariate. The nice thing about moving to Cox pH as compared to, say, serve diff, because we could have done serve diff to compare Kaplan-Meier curves in control and treatment groups. We already know how to do that. But the nice thing about going to Cox proportional hazards here is that we're going to be able to do more general regression kind of things, not just limited to a 2-class problem or a 3-class problem, but having multiple covariates in the model, we can ask what's the treatment effect, adjusting for everything else. Here is the initial one. This is just Cox proportional hazards with the treatment variable in the model. These are the kinds of output that we're going to get comfy with for the next few lectures, working with survival data and doing regression. Notice there is a table of estimates and standard errors and p-values like we've seen in all of our regression exercises. One thing that's different here is that there is no intercept. There is no intercept in a Cox proportional hazards model. The reason for that, I'll say more about it next time, but the reason for that is that the Cox proportional hazards model essentially treats this baseline hazard as the intercept. And the estimation routine that Cox proposed gets rid of that baseline hazard. So there is no baseline hazard that we estimate with the Cox proportional hazards. We only look at the piece that has the covariates in them. That means when we fit one of these things, there will not be an intercept. So all we're able to do with a Cox pH model is talk about hazard ratios. It's the hazard ratio in this case comparing treatment to control. The beta coefficient was minus 0.6844. We said that beta coefficients are log hazard ratios. So if I exponentiate that, 0.5044, this is the estimated hazard ratio. The treatment group has roughly half the risk of the control group. We also have a standard error and a p-value that we can get using maximum likelihood-based estimates. Okay, so we'll keep going with Cox proportional hazards next time. We'll see more sophisticated models, and we'll see how to do likelihood ratio-like tests. And we will also consider checking the assumptions of a Cox proportional hazards model. They are making strong assumptions that we can factor the hazard into a piece that's time dependent but not covariate dependent, and another piece that's covariate dependent but not time dependent. So we have to check that in practice. Okay, I will let you go. See you Wednesday. We'll have a Q&A tomorrow.